Hi, my name is Chris, and I'm a postdoc and associated member of ML4Q, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computer cluster answer questions about their work in the cluster, their research, and the future of quantum. In this episode, I'm talking to Annika Kurzmann, Junior Principle Investigator at RWTH Aachen and associate member of ML4Q. We talk about her work on optical quantum dots in her PhD and bilayer graphene quantum dots in her postdoc, and how she's now bringing this together to optically detect single electrons in graphene. We also discuss the Ruhrgebiet, tenure tracks, and starting a lab during a pandemic. It is my pleasure to welcome Annika Kurzmann on the ML4Q&A podcast. Annika studied physics at the University of Duisburg-Essen and did her bachelor, master and PhD in the group of Axel Lorke, working with quantum dots. She then did a postdoc at ETH Zurich with Klaus Enslin, where she worked on bilayer graphene and graphene quantum dots. She now is a junior principal investigator at RWTH Aachen, working with Christoph Stampfer, and became an associate member of ML4Q. So let's start. You studied at University of Duisburg-Essen, which is deep Ruhr region, deep Ruhrgebiet. I'm also from the Ruhrgebiet, so I can ask you with like in a positive way. Can you say what's a good thing about the Ruhrgebiet?
So the answer you would always get is, I guess, that there are also really nice parts in the Ruhrgebiet. And especially in Duisburg, I enjoyed a lot going to the Sechseenplatte, which is an area where you have lakes, and we biked there like almost every day during summer and went swimming and so on. And I think I also spent a lot of time in a pub close to the university where we could play Fußball. So I enjoyed being in Duisburg, and I enjoyed the time studying in Duisburg.
No, I think indeed the pub culture in the Ruhr area is very nice. Did you also spend some time in Essen, or is the university is distributed between the two cities, right?
During my PhD, I taught sometimes in Essen. So, for example, for physics for chemists, was in Essen. So I had to go to Essen, but usually I think we stayed in Duisburg. Nice. Sometimes for partying we went to Essen, but for the university I didn't go to Essen. No, all our courses were in Duisburg.
Very nice. So let's start maybe back to the beginning. How did you decide to study physics?
I liked physics in high school, where I had a nice teacher, and he also organized that we could do experiments. So students from the University of Duisburg-Essen came to our school, and we could do or perform experiments ourselves and evaluate them. And I really liked what you can do with physics, and that you can learn a lot about nature and how things work.
So like an early engagement with physics at school is quite vital, I guess, to get people interested, you think?
Yeah, I think so. Maybe you need to have this interest already before, so you need to have some interest into physics and nature, and also technical stuff. But I think also school is really important. For me, it was always important how the teacher was. So if I liked the teacher, I liked school, and if I didn't like the teacher, it was not that nice.
I think it was similar for me, and I also got into physics early on. So I would agree with this. I think this is, and we can probably all do more to bring physics to people earlier on. Maybe it's always a good thing to keep in mind, I think.
Yeah, there was also this freestyle physics at the University of Duisburg-Essen, which is quite nice, and high school students come there and do experiments, or solve one problem and show it there. This is also I think something like this is really important to get high school students to do some experiments and also get in contact with the university.
So you already participated in freestyle physics as a high school student?
Yes.
And then when you were a PhD student yourself, did you stay in contact with this program or have?
So yeah, it was invented by Axel Lorke. So I think when I started studying at the university already in the first year, I helped there as a student helper. And I did this every year. So it was 3 days of contact to high school students, which was super nice. And then as a PhD, I did lab tours and organized some of the contests.
Yeah, I think it's really rewarding to see that. You can show physics to people and maybe spark some excitement about maybe seeing a single electron or
Yeah, the high school students always like liquid nitrogen
yes.
in the lab.
No, indeed, that's so. So you basically met the group where you were going to have your scientific beginnings very early on. That's quite special. So what inspired you about the group and what is the main subject of the Lorca group and how did you get in there? Maybe just tell the story a little bit.
There are some different topics, but I was doing, I think, my bachelor, master, and PhD always involved with self-assembled quantum dots. And self-assembled quantum dots are nice single photon emitters, and we also studied in the group the electrical properties, so we could charge the quantum dot electrically, and we did optics, and it was nice to see how this evolved when I was there.
Yeah, let's maybe take a step back. So you have self-assembled means that you have a material where quantum dots just sort of occur in the growth, right?
Yes, they organize themselves.
Yes. So in that case, it's gallium arsenide
and indium
arsenide. So in the Lorca group, you got the materials from another group, or
we got them from Bochum, so also Ruhrgebiet.
Yes. So there's a group that gives you these materials, and you then take this material and you make a device out of it, or you put it under a microscope.
Yeah, so there was not a lot of fabrication. I think in the beginning, you have, compared to the postdoc, you have to do like 2 photolithography steps, which is not a lot of fabrication for me now. So it was mainly going to for the optical measurements, going to optical setup, or for the transport measurements, it was measuring a whole bar.
And so what you then learn about these materials is when you talk with them optically, you see that there is like, I guess if you put this under a microscope, you see like individual emitters, right? So
they are. I mean, under the microscope, they are covered by gallium arsenide again. So you just have a flat gallium arsenide. But if you would start to look at it in a step before in the growth, you would see the emitters.
All right, and then you basically you go around on this chip with all these quantum dots, and you try to find a good quantum dot, I guess, or a region where the quantum dots are kind of good, right?
Yeah.
And then the idea is that you use light to study electrons, right?
Yeah, that was the idea in my PhD.
So how does that work?
So when you have this quantum dot, you can use a measurement technique, which is called resonance fluorescence, where you can excite now an electron hole pair inside of the quantum dot. And when it gets charged, so when an electron tunnels into the quantum dot, this resonance fluorescence quenches, because then you can't excite it anymore because your energy levels change a little bit. And now if you do a time resolve, you measure time resolve while tunneling is possible, you would see that your emitter goes on and off. So always when you have like the charge carrier inside of the dot, you don't see the emission anymore. And when it's empty, you can excite it and you will see a signal, so that you see a nice telegraph noise. So
you're essentially shooting a lot of light, a lot of photons at this sample. You measure which photons come back. Is that the right way to think about it? Yes. So and it has the same energy. And then now you have to use polarizers to separate them. But you can separate the quantum dot light from the laser. And what you see is you see a single electron hopping on and off, right?
Yes. And you can count them.
And you can count how often this happens. And what's the time resolution that you need? What is how long does the electron like to stay in place?
So the growers in Bochum could change that for us, and I think we had milliseconds tunnel rates, but the time resolution of the setup was about 100 microseconds, so we could measure 100 microseconds.
Because you need to measure faster than, of course, the electron tunnels.
Yes.
in order to not miss one.
Yeah, and it's limited by the photon count rate. So when the emitter is brighter, your time resolution will be better, which is quite nice.
And what is the spirit of this research? So now you have a way with light to probe the material science of these quantum dots. Is it more that you think about how you can improve the materials by, let's say, you can, for example, grow the material in different conditions and check how your charge noise changes, like this electron hopping on and off? Or is it more that you think about how to manipulate the light already with there's different angles that you can take to approach the same sort of system, right?
Yeah, so the one is more engineering.
Yes.
And I think it was more the science that was interesting for us, because you can see in this telegraph noise, you get the full information about this tunneling process. And then you can see correlations between tunneling events. So it's quite interesting to really have a look at these single tunneling events.
So the experimental data for this looks like you can just imagine a very long, like a lot of data points which have two different levels, right?
Yes.
Which is like electron there and electron not there. And then you look at how long you stay in each state, right?
Yes.
And you would probably take a Fourier transform, is that right? Or what's if you Fourier transform this, you just get like some time scale for the tunneling, right?
Yeah, but we do it differently. So we do counting statistics. And what you do is, for the tunnel rates, you can just look how long are your times in the upper or lower level. And for the statistic, you cut this long trace in smaller pieces. And for all of these pieces, you count how often charge carrier tunneled. And then you can do statistics. So if you would have always the same distance between the charge carriers, you would just get a distribution. Like I always see for example, 4 carriers in my traces, and you get one peak. But if you have a real current, you will get a Poissonian distribution, because you don't have a regulated current, you have a real current.
Mm-hmm. So the statistics of this tells you the nature of the tunneling process? And it also tells you the interaction of the electron and the light that it sees.
Yes. So if the light influences the tunneling, you could also see it, or you then can see that you get sub-Poissonian or super-Poissonian distributions, which is just wider or smaller or distributions than a Poissonian distribution, and then you can get more information about interactions.
I guess you don't study one of these quantum dots, right? But you need to study.
No, we study one.
Oh, really?
That's
just
also
one.
the
Always
advantage of the optics, yes.
No, but what I mean is do you study one, or do you then also look at, in each sample you will have several quantum dot candidates, right? You can probably move around with your microscope and you find a quantum dot here and a quantum dot there. How similar or different are different quantum dots in the same sample? They
are very similar.
Okay.
So I think the same sample that I used during my PhD was cooled down afterwards again, and it looked quite similar.
Quite similar, okay. So it's not like that there's a strong influence of the local environment of this quantum dot, but it's really something that is conditioned by the growth, like it's something that is in principle engineerable.
Yeah, so the tunneling is engineerable, yes.
During your studies, you also spent some time abroad at Princeton. How was it to go from Duisburg-Essen to the Ivy League and from the Ruhrgebiet to New England?
The weather was super hot. I think I never experienced something like this. Yeah, and the weather was nice for 2 months, which was super nice.
And this was a university student exchange, right?
Yes, it was an exchange. So I went to Princeton, and while I was in Princeton, 2 students from Princeton came to Duisburg. And also from Bochum and Dortmund, so from the Ruhr universities, students went to Princeton as well. So we were 3 people from the Ruhrgebiet going to Princeton and 6 Princeton students coming to the Ruhrgebiet.
And how did the exchange work? Did you guys meet each other and discuss the experience? Like the incoming and outgoing students?
I met them before I left to Princeton. So, I mean, they went to the group where I was a master's student at this time, or a student assistant at this time. So they already arrived a few days before I left to Princeton, and I met them.
Very nice. So how was this student exchange experience? Is this like an enriching experience, or did it also give you some new insight into research topics?
Yeah, so I never worked with quantum cascade lasers before, so I saw something completely different. It was also interesting to see how university life is in the US. And I think it's also different to how it is in Germany, for example, or also in Zurich. But I went there at a time where the university was closed, so there was a summer break, and the students were not in Princeton, but a lot of summer exchange students were there.
So it was not as many Americans, but people from all over that you could meet there, I guess.
Yes.
And you also had hosted people coming back from Princeton to Germany afterwards, right?
Yeah, so I participated in the first year of this exchange program. And the years afterwards, I was a PhD student. So the students coming from Princeton were working with me in my lab then afterwards. And I could supervise them and work with them together.
So that's, I guess, a good teaching experience, like a good experience supervising relatively short and concise student projects.
Yeah, it was always nice to meet new people also from the US and to teach them and show them what we are doing in the lab. And usually they didn't have a lot of experience in the lab, so you could start from zero and explain them everything and give them small projects that they could couple laser for the first time and things like this.
I think this is something that the German physics education actually does relatively well, right? Like that, because we have already in the bachelor project usually a half a year or like a few months, but up to half a year working experience in the lab. And I think that's really something that not all other countries have, right? That people already have lab experience at the bachelor level.
Yeah, I also think that this is super nice. And also, I mean, in Duisburg, for example, you could also always work in the lab during the bachelor's and the master's. So the student job was working in the lab. You could already do something for your career, but also get money that you needed as a student.
Yeah, and indeed, like I think that so in many other places, the master's project is also shorter, right? So you have less of, I mean, if you have just like if the master's project is as long as the bachelor student project is in Germany, people have like there's less opportunity to have projects where things could go wrong.
Yeah, and I think also when you supervise master students, for me it was always in the beginning you teach them a lot, you do a lot with them together, but after a few months, I think it needs a few months, they can also do work themselves, do experiments themselves, and they just learned how to do it. So if you then stop with the master's thesis.
Yeah, I agree with this. I have to say that as a supervisor, I definitely prefer master's projects to bachelor projects, because the shorter projects, you spend a lot of time teaching somebody, then you have to let them go at the moment where they could do something independently. With the master's project, you really, it's really, I mean, of course, teaching is also something worthwhile, but you also as a supervisor, maybe you get a bit more benefits from teaching a master's student.
Yeah, but maybe if you did a good job during the bachelor's, they come back for the master's.
Yeah, exactly. So, I mean, of course, you can, as a lab, not afford to only take master's students, because otherwise, if you take no bachelor students, you will get no master's students.
Yes.
How was your PhD experience then? So we talked a bit about what you did. How did you do it? So you have... did you start in a lab that was already doing a lot of this research, or did you start it up? I guess there's many PhD trajectories, right?
Yeah, I mean, there was a lot done already with self-assembled quantum dots, but this measurement technique of resonance fluorescence was not established. And there was a postdoc, or now assistant in the group, who was in Cambridge before, in the group of Mete Atatürk. And he learned there how to do resonance fluorescence. And when I started my PhD, he came back from Cambridge. So we started to build up the lab in Duisburg also to do resonance fluorescence. Yeah, and we started with an empty lab. We had this AtoCube setup that was 10 years old, so it has the serial number 002. So it was really the first setup that were built from AtoCube, but not used a lot in the lab. And we could use this.
And then you built an optical table, so you're quite familiar with how to set up an optics lab from scratch.
Yeah, I can couple lasers.
How automated are the optical labs? I've visited a few different labs by now, and I think it's always fascinating to see like these. I don't know if you visit like MPQ in Munich or maybe the groups in Bonn. Optical tables can go from people adjusting mirrors by hand to a completely automated setup that is like essentially encased in glass and that nobody touches. So what's your preferred optical table? Was it very hands-on or?
Mine was still very hands-on, yes. So I had to change the laser frequency by hand. I could change it a little bit with the computer, but then also I had to suppress the laser with the polarizers. So, and the polarization always changed a little bit when you would change the frequency. And then I always had to play around with the polarizer. So I spent a lot of time turning polarizers and
aligning beams. And yeah. I remember in my bachelor thesis, we sometimes just needed to knock on the laser for it to frequency lock again. It's also quite fun. I think lasers can be a bit temperamental, right?
Yeah, so I just had my laser just was bought from Toptica, so it just worked. And but we also had a teaser, and to align this one was really hard, and we needed a postdoc from another group to do this.
All right, very cool. So essentially, this is a way to optically look at how electrons behave and to learn about the physics of light-matter interaction and of electrons and matter. So this was your PhD work. Mm-hmm. And now you decided to go, after your PhD, you decided to go to ETH for a postdoc. How did you decide where to go next after your PhD?
Yeah, I was searching or looking for different groups, and then Klaus was my co-examinator for my PhD thesis, Klaus Enslin. And at one point he asked me if I would also like to give a talk in his group, and it was an application for a postdoc. So, and I really liked the group because they told me that it's nice, or the PhDs told me that it's nice to work there. And there are also a lot of social activities, and it just sounded like a super nice group. And also the research was interesting. And I knew his group or his works quite well because he was also counting electrons, but in transport, not in optics. Mm-hmm. But so I always looked at his papers or the papers from his group for different stuff for counting electrons.
So, but you could not continue with photons in his group.
Yes, there are no photons. Now there are microwave photons, but no.
But at the time there were no photons. So you needed to change from looking at electrons literally through a lens to looking at electrons through electronics, I guess.
Yes.
So and also the quantum dots changed.
Yes, the material also changed.
The material changed. So you went from gallium arsenide to bilayer graphene.
Yes.
Bilayer graphene is probably one of the most hyped materials of the last few years in physics, right?
I think twisted is even
maybe twisted bilayer graphene. But so let's talk a bit about. Graphene itself also was quite a hype. So let's start with what is graphene?
Graphene is a two-dimensional material. So there are a lot of two-dimensional materials now. And it was found that it behaves quite nice, the mobility is good and so on. So there was a lot of research after the Nobel Prize they got to graphene, or to Guy Menno-Zelo for finding graphene. And it's also, I mean, you can just get a crystal and exfoliate it. So to just make graphene or bilayer graphene is quite simple. But yeah, we make devices out of it, and I think this is a little bit more difficult.
So can you just explain the work of a graphene scientist? There's the Scotch tape method, which is the Swiss knife of 2D materials, I guess.
We didn't use Scotch tape anymore. It's blue tape now, so it's a blue tape because it's supposed to have less residuals. But then, yeah, you have a big piece of, or rather big piece of graphite, and you put it onto your tape and press it together sometimes, and then you can put it on your substrate, and you have graphene or bilayer graphene or thicker graphite.
You rip off the tape and you rip off a single layer of.
Sometimes, yes.
Material, yes.
So then you go to the microscope and you just search for the right
size.
Yes.
So when you look at these, so you have the Scotch tape, you turn it around, you put it under a microscope, and you can see, in this place, or maybe you first transfer it to another chip, right? So you rip off the tape, and then you put it on another chip, and then the graphene.
No, you leave it on this chip. You just
take
off the tape, and then you leave it on this chip.
Okay, so you look under the microscope, and now you can see different layers of this graphite thickness. And with the microscope, you can see whether there's one atomic layer or two atomic layers.
Yeah, if you are a little bit experienced, you can see if you have a monolayer or trilayer or bilayer.
How do you see a monolayer of atoms?
You can see it because we use a good substrate. It's silicon with silicon oxide, and if you choose the correct thickness of silicon oxide, you can see it from the contrast. So it's just a reflection that helps you to see it.
I still find this marvelous. It's kind of fascinating, right? Like, people have taken so long to see atoms, and in the end, all you needed to do was take a piece of tape, rip off a piece of graphite, and you can see whether there's one layer of atoms or two layers of atoms.
Yeah.
It's a bit ironic.
Afterwards, you think it's easy. Why?
Yeah, exactly. Like, people didn't stumble on this for a long time, right? I mean, for a while, people didn't think 2D materials were thermodynamically stable, right?
Mm-hmm.
So, I mean, now this is all very easy, but people didn't realize this people could have realized this 50 years ago. Like, the equipment that you use is not,
Yeah, the tape is available.
And the microscopes were also already available,
yes.
Yeah. It's not a super fancy microscope, right?
It's a normal microscope.
So this is how graphene started, and basically already this graphene had pretty good properties, right? Like, even at the beginning. But then along came hexagonal boron nitride. And how did this influence the graphene research?
It was quite important because there was always dirt on the graphene, which is not good for the properties. So after encapsulating it into hexagonal boron nitride, the quality of the graphene improved a lot.
So you're making a sandwich.
Yes.
And hexagonal boron nitride is also Scotch tape. So
yes. So you get crystals from Japan, and then you do the same. You exfoliate them with the tape and put it on a substrate, and then you can also search for flakes for the correct thickness. And after that, you go to a microscope where you have a transfer arm,
mm-hmm.
and then you can start to pick up different flakes and stack them on top of each other.
Is there another way of making high-quality graphene and boron nitride that is less manual?
It can be grown, but I think there are still some problems for our research, because we have really small structures that you get defects or grain boundaries and so on that we don't like when we do our devices, make our devices. So yeah, for us, I think at the moment the exfoliated graphene is the best choice.
So 2D materials is very manual work, I guess, because you have to do a lot of...
I mean, now at ETH and also here in Aachen, they started to program programs that can search for the flakes for us. So you just have to put your substrate below the microscope, and then it's scanning the wafers for hours. It's not too long, and then it gives you where you can find your monolayers and bilayers. And I think there are also already machines that can stack flakes on top of each other with the robot arm in Japan.
Wow, that's amazing. But yeah, it's basically the success of 2D materials on the one hand was that with relatively little equipment, a lot of groups in the world could immediately start doing this, and they did. But yeah, it was for a long time this quite manual approach where you have to do this fabrication. Do you like this part of the job? I mean, it's a little bit fiddly, but it's also...
Yeah, I enjoy it, yes. I mean, for me in Zurich, for example, it was a smaller part, so the stacking of one stack took about 1.5 hours. And then the fabrication in the clean room afterwards was 2 weeks, so it was just the smaller part of fabricating a sample, but yeah, it's fun.
We already said that it's bilayer graphene, not single layer graphene. So at the moment we're moving away from like having this absolutely like this one layer of atoms to having 2 layers of atoms. What is the important difference between 1 layer of atoms and 2 layers of atoms?
If you have a monolayer graphene, I think many people know that there is a linear dispersion. So you will not have a band gap, and then you can't do any electrostatical
it's more like a metal
confinement.
Basically.
Yes. But in bilayer graphene, you can open a band gap, and therefore you can get insulating areas in your device, and you can start to build devices like quantum dots electrostatically.
Because you can put voltage somewhere, like below you put below the graphene, the bilayer graphene, you put like metal somewhere in some parts, and you put the voltage on there, and you can get rid of the electrons in some parts.
Yeah, you need 2 gates to do this, but I mean you need the back gate and the top gate, but then you can.
So if you put this together, so the bilayer graphene gives you a 2-dimensionally confined electrons. And then you use these gates to take those 2D electrons and make quantum dots.
Yes.
Which is a slot for 1 electron, right?
Yes.
And it's not so long ago that people succeeded in having a single electron in these graphene islands, right? So that's a really important step in this research.
Yeah, so I think the first quantum dot was built in the group at ETH when I started my postdoc there. One PhD made the first quantum dot, and I think it was 2017, so it's just 4 years ago.
And what's special about having a single electron compared to having many electrons?
It's getting super complicated if you have many electrons. So we studied, for example, the energetic structure of 1 charge carrier or the excited states and 2 charge carriers. But already after that, if you have 3 charge carriers, it's already getting complicated. And also, if you want to build a qubit, you need less charge carriers.
What's the roll from a quantum dot to a qubit? What's the road from a quantum dot to a qubit?
In principle, a quantum dot is a qubit. You just need to show some properties that it has to fulfill. So, you need a spin, for example, as that you can save and that you can store and that you can control inside of the quantum dot. And you need to show that you have long coherence time so that you can store the properties inside of the quantum dot for a long time.
Mm-hmm. And people have been, like these quantum dots, making quantum dots out of these 2-dimensional electron gases has been done for a while in first, I guess, gallium arsenide,
mm-hmm.
and then in silicon, in different material combinations with silicon. Where does graphene fit in this landscape of different 2-dimensional electron gases? What are the advantages and disadvantages?
The advantage compared to gallium arsenide, for example, is that you expect for a graphene that it has not such that the environment doesn't have such a big influence, for example, on the spin. And for silicon, I think there's always a problem with the valley degree of freedom, which is more tunable in our quantum dots or in the bilayer graphene quantum dots. And I think we could also show now that the valley degree of freedom is a quite good quantum number also in bilayer graphene quantum dots, so it's not that bad.
So the physics of electrons in graphene, in bilayer graphene, is already quite complicated because the electron has a spin and there's this additional degree of freedom which is due to the crystal structure. Mm-hmm. What do you need to do to either control or play with these degrees of freedom in order to, basically what you want to do is you only want to have one degree of freedom in the end, which you make a qubit, right? Mm-hmm. So is it clear yet which of these degrees of freedom one should choose for making a qubit in graphene?
I think it's not completely clear because we found that the ground state is a spin triplet state, so at zero magnetic field. But then when we increase the magnetic field, we can have a spin triplet ground state. So you would always need the magnetic field to have the spin as a qubit. But the valley, it looks like the coherence times are not that good. When we look at spin blockade or at currents through double dots, it looks like that this quantum number is not as good as a spin quantum number.
So in order to control the valley degree of freedom, what can you do to manipulate, so the spin of the electron is manipulated with external magnetic fields or with, for example, currents which generate magnetic fields next to the dot, I guess?
Yeah, at the moment we just use magnetic fields, so we have this huge magnets in our fridges and we can just apply magnetic fields. And the nice part is that the spin can be manipulated by the absolute value of the magnetic field. So if you now apply a parallel magnetic field, for example, you can manipulate the spin. And the valley degree of freedom is also manipulated, but just with the perpendicular component of the magnetic field. So if you apply a magnetic field perpendicular to the sample, just this valley is changed.
Is there other ways? So we already said that electric fields are important to control where the electrons are and where they aren't. Is there other ways to manipulate the valley degree of freedom, or?
Mm-hmm. Yeah, we have one paper about it, that you can change the size of the quantum dot with the gates, and with the size of the quantum dot you can also change the valley splitting.
Is it as simple as if I don't know, maybe this is too naive, but if I imagine a quantum dot, you have a bunch of atoms of the graphene on which the quantum dot lives, right? How big is the quantum dot? How many atoms of graphene are inside one of these quantum dots?
Our quantum dots are about 100 nanometers, mm-hmm. I would say, in both dimensions. So now we have to calculate how many atoms.
So maybe 1,000 by 1,000 atoms, something like this.
Yes.
Is it that if you have 1,001 atoms or 1,000 atoms, that changes the way that the valleys participate?
I think the change of size has to be a little bit bigger than
so it's not having one extra atom that would make the difference.
No, I don't think so. So we tune the size by a factor of 2, mm-hmm. I think. And then we can change the valley G factor by a factor of 3.
So let's also quickly say that the G factor is the way that the spin interacts with the magnetic field, right?
Yes, it's like when you apply a magnetic field, you can split the spin down and the spin up state. And yeah, that's what.
And one of the advantages of graphene is that your G factor is big, which means that you need smaller magnetic fields. Is that right?
For the valley degree of freedom, it's big. Yes, you need small magnetic fields to split it. I think already at 0.2 Teslas, the valley is the ground. The valley splits so much that it,
All right. So there's basically people are starting to understand the physics in graphene quantum dots better, and we're starting to find out if we can make them into useful qubits. That's the current state of the research.
That's the current state, yeah. There was just a paper like a few weeks ago from Christoph Stampfer's group, and also the group at ETH is working or has measurements to on the relaxation times, for example, which are now, the measurements we are doing and the state of the quantum dots.
Cool. So it's really sort of a new contender in the world of spin qubits and quantum dots.
We hope so.
So let's maybe, there's these, we talked already about the bilayer graphene. So this is what you get when you rip off the tape and you accidentally take 2 layers of the material. But you can also make 2 layers of material by ripping the tape off twice and getting each time 1 layer and putting them on top of each other. What's the hype around the slightly twisted bilayer?
It was found to be superconducting. Mm-hmm. So it has different properties, and you can tune it with the electric field. So you can go from a mod insulator to a superconductor just by changing the gate voltage. And I think it's the first material where you can do this. Yeah,
I think it's quite. Even I'm not in this field, so that's also why I'm struggling with some of the questions, I guess. You can already see that even as quantum physicists go, the different fields are very, very different. And of course, once we have a qubit, it's easy, but all qubits are different. But everybody in the physics world noticed that there was 2 papers back to back in Nature or Science, Nature, from the same group, which is, I think, quite remarkable in that case. And that was this superconducting and insulating graphene.
Yes.
Was this even measured on the same device or slightly different ones? Probably slightly different ones.
I'm not sure.
Me neither. But so what people do is they take this graphene and they basically put the one graphene on top of the other one at a slight angle, right?
Yes.
And you can play with this angle.
Yes.
And do you want small or big angles?
For the magic angle, so to get it superconducting, you want a small angle. Mm-hmm. But you can also, at ETH, they also did slightly bigger angles, like, I guess, 4 degrees or something like this. Mm-hmm. And then, you also investigate the properties you get. So you always get different properties when you change the angle. And
so basically you have a material that can, what is the special thing that changes in the material? How can the slight angle make graphene superconducting?
It's a band structure that changes because of the angle.
And what's the special thing about, like, what's the special thing in the band structure that
you get flat bands? That's what you always hear.
I guess.
Yeah.
And why are flat bands special? Okay, I also.
Kein Experte von Twisting.
Okay, we don't have to go there. I think isn't it like electron interactions that somehow, weil ich finde das alles lange her bei mir. Es ist, wenn du ein flaches Band hast, dann geht deine Elektronenmasse ist die Bandkrümmung.
Ja.
Also ich glaube, dass die Elektron-Elektron-Interaktionen explodieren, weil du halt auf einmal unfassbar viele ich weiß nicht, ich bin gerade nicht sicher, ob es mit der spezifischen Masse oder mit der Density of States zu tun hat, weil wenn du ein sehr flaches Band hast. Keine Ahnung, ich hab auch nur ein bisschen reingelesen, ich bin auch kein. Okay, but okay, so we don't have to do the magic angle. But so at any rate, so graphene is an exciting new contender for quantum dots, and the research is happening right now. So I guess in the next 2 or 3 years we will probably know much more about this than we do now, right?
And hopefully see the first qubit.
Yes. So let's do a quick intermission with some rapid either/or questions. So let's start with Duisburg or Essen.
Duisburg.
Duisburg, very good. The Rhineland or the Ruhrgebiet?
Ruhrgebiet.
I also think I prefer the Ruhrgebiet. The Rhineland people are very fond of the Rhineland, while the Ruhrgebiet people are a bit less fond of the Ruhrgebiet.
Yeah, I always like this that you have, you always can say, okay, where I come from or this region is not super nice, but you still like it.
Yeah, no, I have the same. And I agree that I think it's very, very green and has a lot of nice spots. It's a lot less touristy maybe also.
Yeah.
Electron or hole?
Electron?
Yes. And then single electron or single photon?
Single photon.
Do you prefer optics or electronics?
Tough question.
Yes.
Optics.
All right. And the clean room or the optical table?
Optical table.
All right. And do you prefer the graphene or the quantum flagship? As flagships go.
Graphene.
All right. Very good. I think so. Let's now talk a little bit about your plans for the future. So you're starting a new research group, which combines your PhD and your postdoc work, and that's already super cool. I think not many people can bring things together so well. What is the key thing about the graphene quantum dots and the boron nitride and all of this, which makes it possible to bring everything together?
It's 2D materials, which is super nice that you can stack all materials you want or that you can exfoliate. You can stack all of them on top of each other and use the different properties of all these materials and combine them. Like hexagonal boron nitride, which also has some defects that you can use as single photon emitters, and then it's already in our bilayer graphene quantum dot samples, and you can form the quantum dots in bilayer graphene and still have the emitters.
So it's really a happy accident that the materials that anyway work together very well also allow you optical access.
Yes.
And obviously you also convinced a lot of other people that this is a good idea because you got a junior principal investigator position to work on this. So how was the application process for this like, and what does it mean to get such a position?
I had to apply with a small proposal. It was just a few pages. And I think this was 1 month before Corona started. And then I think my interview was during Corona, so it was online. And I was invited for this interview where I had to present my idea and got some questions from different people from RWTH Aachen.
And so this junior principal investigator position is a 4+1 year position. Is this the German system is kind of in shift right now as the way of how to become a professor or permanent academic, right? So where does this lie as far as there's the habilitation, there's a tenure track? What exactly is this position like?
I think it's somewhere in between a postdoc and a junior professor, because I have my own money for my own position and for one PhD student, so I can have my own research, but I'm also embedded in the group of Christoph Stampfer. Yeah.
So it's some new middle way to allow people to it's not related directly with the tenure track, right?
No.
So it's not exactly to explain to non-academics. Tenure track in the US means that you get a job, and if you don't do something stupid for a few years and are moderately successful, you become a permanent professor.
Yes.
In Germany, this does not exist in the same way, right?
The tenure track?
I think there's no... I think most German tenure tracks don't have this guaranteed hiring, right?
Yeah, you get these evaluations, right, in between the tenure.
I think in Germany you can get a junior group, but there's no guarantee that you can stay at the same university. Like you do it for a few years.
I think some of the tenure tracks also have a fixed position that you can get afterwards, but not all of them.
Exactly, not all of them. So the German system is kind of in a weird, like it's a mix of tenure track and sort of having a junior a junior group without guarantees.
Yeah.
Like let's say it like this. And there's also the habilitation. Can you say something about what are the strengths and weaknesses of different parts towards like a more permanent job in academia?
I don't have a permanent job, so
No, of course. I mean,
I don't know how to get it. Yeah, I think the habilitation is something very German, right?
Yeah, apparently.
You don't have it in other countries, and I don't know how important it still is.
Yeah, it's weird. I'm also a postdoc, so I'm also interested in this, and it's not something that anybody ever tells you, right? It's not like a professor goes to you and says, okay, in order to become a professor like me, what you should do is this, right? Or at least this doesn't happen often. So the habilitation indeed is something that in principle, you write another thesis, right?
Yeah, so the habilitation is in principle that you are allowed to teach at a university. So afterwards in Germany, you are a Privatdozent. And yeah, you have the right that a professor has to teach at the university, but you don't get the title.
Exactly. So so basically you can do your research as a postdoc for a while. You write another thesis and you're allowed to teach, but there's no guarantee of getting a job.
Yes.
Which is kind of why this is becoming less attractive to people, I think, right? Like having like the advantage of your position, for example, is that you already have 5 years to, stay here and make things work.
Yeah, and to have my own project and also starting with some money for my project. I mean, I applied for more money, but I already have money to do
start
something.
No, indeed, that's really important. So it's like a different, like the RWTH Aachen University started a new way to give to give people a better road towards becoming essentially professors later on. So what role does the ML4Q cluster play in your in connecting you with other scientists, but also with funding opportunities?
So beginning of this year, I applied for an open call, or maybe end of last year. So I got it this year so that I could also buy a new laser and some equipment that I needed, which was quite important for me. Because, I mean, I have some money, but not enough to buy everything for my lab. And there are also these regular meetings, which are quite interesting because I can see what other people are doing with single photon emitters and what groups in Bonn and Köln are doing. And last month, I also went to Bonn once and had a look at the labs of other professors, and we talked about what we could do together. So I think it's a quite nice environment, and there are people that can help me, or we can cooperate and make the single photon emitters and 2D materials work.
Yeah, indeed, it's really important to have, on the one hand, just people who have solved the same problems before.
Yeah, but just in different material systems.
Just in different material systems, yes. Because, I guess you cannot know everything, right? Like
you never know.
You never know everything. So it's always good to have the possibility of getting advice from somebody who has done something similar. So how is it like to start a new lab at the height of COVID?
Yeah, I think it's not the nicest thing because there are just some delivery problems that are occurring now, and I think I had delivery times of more than half a year for things where you usually would have 1 month or something like this. So I think this is a quite big problem. And yeah, what also was difficult or is difficult that you don't see a lot of people. I mean, this interactions that you usually have at the university is not completely back to normal.
Yeah.
It was okay during the summer, and now it's getting worse again. So.
But we visited your lab a little bit earlier, and you have an optical table, you have a cryostat. It looks like you're ready to start. So what?
Yeah. So we could do already some measurements because this cryostat and the optical table was already there. I have it from Christoph Stampfer, who was measuring or had the PhD student measuring there before. So I was quite lucky that there already was equipment that I could use.
So in that sense, also this principal junior investigator position is quite advantageous because you have a larger group that you can start out with, and because otherwise, if you start a junior group maybe in a place that doesn't already do optics, you have to build everything from scratch, and then the corona delivery problems would hit you harder, right?
Yes. So I think this was also one requirement for this junior principal investigator, that there is a host at the institute that can already give you some, or has some equipment that you can use.
All right. So now, what are your immediate scientific plans? What is the next experiment that you will do?
The next experiment is just shining a laser on a bilayer graphene quantum dot. So that's also one advantage of being part of Christoph Stampfer's group. They are also doing bilayer graphene quantum dots. So I can get just one sample from them at the moment and shine a laser on it and see if we see optical effects in the transport measurements.
So what you need one of these optical defects that is close enough to the quantum dot such that the defect will react to the quantum dot, right?
Yeah, that would also be a plan, to have a defect close to the quantum dot so that by Coulomb interaction you can see an influence of charging the quantum dot on the emitter.
If you do this, would you first look at the boron nitride and then decide where to put your quantum dot, or do you or do you just get lucky? Like how?
I think in the end you have to do it like this. You have to search for the emitter before, and then fabricate the sample around the emitter.
Yeah. Okay. And so you right now, I guess you're trying to understand the different emitters that you see there better
and try different materials of HBN, so they are grown in different groups and with different methods, and we are looking at different samples now and see which emitters are more stable or less stable that can be used for.
So basically, once you find the right boron nitride, which is the insulating material, then you just put the graphene quantum dot next to it, and then you can see the single electron with your optics.
Hopefully, yes.
Very good. So you have already one PhD student. How do you feel about supervising a PhD project? You and we have been PhD students not so long ago, so we feel the weight of the responsibility, I guess.
I like it. So at ETH, I already worked with a few PhD students, and it was always super nice for me to supervise them. So 2 of them started at the same time at ETH, and I showed them how to do everything, and it's nice to see how they evolve, and at one point they know more than you know.
Yes.
So I think also now with a PhD student, it's just super nice to work together and to build up the lab. Yeah.
What do you look for in a PhD student?
I think for me it's important to see that they like what they are doing. So they must like physics and fabrication, and so just they have to like their job.
Yeah.
I think if they like their job, you would always get them to do something that in the end will be. And
it's also much more enjoyable to mentor somebody who enjoys the job.
Yeah, and if you don't have to motivate them all the time.
Yes. So there's mentoring and there's teaching. Are you excited also to do some teaching, or do you have to do some teaching in your position?
At the moment, I did some lab supervision, but I'm also happy to do more teaching. Now I just built up the lab, so there was not that much time for teaching, but I also like to teach and to do exercise classes, or also, it would be nice to give a lecture.
Do you have any advice for postdocs wanting to stay in academia and asking for a friend?
In which For which situation? For teaching or for...
No, more in general.
I don't know if you can give a real good advice.
It's the jungle, basically.
I just always did what I like to do, so I can't really say, you have to do this or this or...
And maybe we can just briefly talk about the percentage of women in physics. So there's the situation that the higher you move up in the academic hierarchy, the fewer women are there, which is bad because, I mean, in an ideal world, there would be at least as many women in professor positions as there are in starting to study physics, right? What can the community and I guess the majority of men do better to improve this?
Yeah, I'm not sure if it is the interaction with male colleagues or if it's just a way of being successful in academia, because I think for many females it's also that you have to change your location or to be flexible to change your location, and that's not really combinable with having a family. So I think that's something where
it's not so easy to fix,
where women would, after a PhD, say, okay, that's more important now for me. So I think it's hard to change this.
Yeah. So you don't think that it's generally the male-dominated environment that is keeping women out, but more the career?
Some female colleagues told me that they would also, when they search for a research group, they would look for other female scientists in this group and then decide if there is no woman in this group, they would decide not to go there because they are afraid that the environment might not be nice for women. But I don't know. It's hard to solve this problem to put a female in all of the different groups.
Yeah, I mean, obviously, it's a very difficult problem to solve. Obviously, another thing is that we have to engage women at the high school level to have more women to start in physics. But indeed, we also probably have to do more to keep them in the field at the higher levels. And I mean, it's true that the family priorities for men somehow work slightly differently than for women at this moment still. So that maybe that drives part of the postdoc time is really you're usually in your early 30s and that's definitely a problem. I think that's,
Yeah, but I think you can also, if you have a PhD student, a female PhD student, I think it's also important to motivate them a little bit to also go into the academic career, because some of them just think they are not good enough. And if you motivate them and tell them that they are good enough, maybe more of them would say, okay, I tried.
Yeah, I think it is really a problem that if you ask 10 men how competent they are and you ask 10 women how competent they are, you get more positive answers from the men, and maybe then if you test them on it with some test, you will find that the women perform better, right? Like that seems to be something that happens. So I don't know if it's possible to just on the one hand maybe get men to be a little bit more self-aware, and also get women to be a little bit more self-aware of their strengths.
I don't know what is better.
Would be good if both of these things happen, I guess. I think thank you a lot for discussing your career and going over these things. Do you have some things that we didn't talk about that you would still want to talk about?
No, I'm happy.
All right, and thanks a lot. And thank you for discussing.
Thank you.